Welcome to our video presentation on the phenomenon known as double descent. To understand this phenomenon, let's review the concept of bias-variance trade-off in a typical machine learning model. We are going to talk about this paper. This error can be divided in three components. Bias, which represents the average difference between the prediction and the true value. Variance, which indicates how much the prediction vary on average, and noise or irreducible error. Here we have an example, an illustration. The complexity of a model affects the balance between bias and variance in the error. When the model is simple, it's stable but not very explanatory, leading to underfitting, high bias, and low variance. On the other hand, complex models are adaptive but not very generalizable, resulting in overfitting, low bias, and high variance. For optimal performance, models of moderate complexity can be used to minimize the error. This is known as the sweet spot. However, very complex models can exceed a very low or negligible prediction error. When the number of parameters exceeds the number of training samples and the training error is very close to zero, the prediction error continues to decrease, occasionally reaching error values lower than the optional point. This phenomenon is known as double descent. Why this happened? According to Mirkhan-Belkin, who first proposed the generality of this phenomenon, considering broader classes of functions allowed us to find smoother and simple interpolation functions, improving the performance of classifiers. To illustrate this, let's consider a small example using a linear regression model. This example demonstrates that the double descent phenomenon can be observed in other types of models as well. We can see that as we change the number of parameters in our linear regression, the test error initially decreases. However, if we continue increasing the number of parameters, we reach a first minimum test error. After that point, the error starts to increase because the model begins to overfit the data. Nevertheless, if we further increase the number of parameters, the test error starts to decrease again and eventually reaches a new minimum. Now let's observe the linear regression model behaves when we add more parameters. Here we have a small animation. Can we assure double descent, at least in linear regression models? So to generalize, we need to ensure this behavior under the following conditions. First, small but non-zero singular values do not appear in the features of the training data. Second, the test data lies entirely within the subspace span by only a few principal singular directions. And the last one, the best possible model within the model class make no errors on the training data. Double descent does not occur when increasing the complexity or parameters of the models. Epoch-wise double descent is a phenomenon where the test error of sufficiently large model decreases, then increases near the interpolation threshold, and then decreases again over the course of training epoch. A study by OpenAI shows that the different models' size exhibit different patterns, with larger models transitioning from underparameterized to overparameterized regimes during training. This phenomenon is robust across different optimizers and learning rate schedules, and this is accentuated with label noise. These findings challenge the conventional wisdom that the training consists of two phases, where the network first learn a function with a small generalization gap and then overfits the data. Instead, the error may decrease again and achieve a lower value at the end of the training. Sample-wise non-monotonicity explores the impact of varying the number of training samples while keeping the model and training procedure fixed. We observe two distinct effects when increase the number of samples. Firstly, the expected expected effects is that increasing the number of samples reduces the area under the curve. Secondly, it has the additional effects of shifting the curve to the right, causing the model complexity at which the error peaks to increase. It's worth mentioning that in certain scenarios, these twin effects combine, resulting in a regime of model size where more data actually impacts the test performance, as displayed in this figure. Okay. As a wrap up this presentation on the double descent phenomenon, we invite you to explore the OpenAI papers for further insights. So, thanks for watching.